Okay, okay. Can you guys see my slides?
Yes.
Good. So we talked last week about IoT in general and what an IoT system actually is and what are its main components. We also spoke briefly about some major IoT protocols employed today in these systems and what are their key particularities. Now, let's talk a bit more about communication models in IoT. So, what does a communication model mean? It's a way two entities, maybe a client or a server or two peers, can communicate. And we've got, I think, the most familiar model to you would be this client server model, in which you have two entities basically. You have a client, you have a server. Usually the server has available more resources than the client, and whenever a client connects to a server, it's regarding the resources that the server has. So the client requests some sort of resource and the server responds with that resource. So it's a communication model where you have these requests from clients, and of course it's a connection that can scale to a lot of clients, so multiple clients, maybe thousands, hundreds of thousands of clients at one time connecting to a single server or to multiple servers. But you can distill it down to this. Whenever the server receives a request from a client, it decides how to respond. So it's totally up to the server to actually fetch data or the resources that are requested by the client, and prepare the response and then send the response to the client. Or if the resources are unavailable, then the server can decide to actually send an error message or some sort of warning to the client. And it's a model which is adopted by the web in general. So whenever you have a connection through the internet, you usually adopt such a model of a client server paradigm. Now, there's another one which is typically used in IoT whenever you want to publish a lot of data and you don't necessarily need a connection to a server which has available only one type of resource. So this is the publish subscribe model or pub sub model that we've discussed briefly about in the lecture last week. So what it implies is you have a publisher of data. So usually the publisher sends messages to different topics. These topics can be varied. So you can actually send, I don't know, sensor data, for example, and temperature could be a topic, and then humidity can be another topic, or light intensity or whatnot could be different topics. Usually the topics are not available at the publisher. So whenever you connect in this model, you do not connect directly to the publisher, because the publisher might have some very limited resources. So it cannot scale this communication model where you have multiple connections to it. It could be a very simple IoT device. I don't know, maybe a 8-pin microcontroller with very limited memory and very limited connectivity capabilities. So then in this model, the publisher publishes the messages to a broker. And the broker is, let's say, analogous to the server in the previous client server model. So the broker has these topics, which are aggregated from messages sent by the publisher or the publishers. There might be multiple publishers on these topics. And then you have consumers or subscribers, so to speak, which actually adhere to this data. So they can connect to the broker and they can subscribe to one or two or multiple topics. So there can be, multiple consumers connected to the same topic, or there can be different consumers connected to different topics. It's a very flexible model in which you can actually create very easily a connection between multiple viewers of the data. So you and everything is actually mitigated through this broker. So this broker is the middleman in this transaction between the publisher and the subscriber. Again, it's very familiar to IoT systems because it doesn't imply that the publisher needs to be very resource heavy. So it doesn't need to be a high performance computing system here. It can be a very low power, very low cost system that actually sends this data. And also it doesn't need to be, the publisher doesn't need to be always available in this. So whenever the publisher publishes data, and it can be once every second or once every month, for example, you actually have this model which works. Again, it can scale very easily to multiple publishers that send data simultaneously to the broker. Another model, which is also very used in IoT, is the push-pull model. And it's in a way similar to the pub-sub model, but right now the broker is replaced by message queues. So again, you have the publisher, which can be a very low-cost, low-power device. And then this one actually publishes data to different message queues, which are stored on one or different servers. So they can be stored independently, or they can be stored in the same place. So what these message queues do is they actually come and buffer the data so that the consumers can subscribe to the data, and they can pull messages from the queue. So it's a push-pull model in which the publisher pushes messages to publication queues, and then the consumer actually comes and pulls messages from the same queue. Again, it can easily scale to systems where you have thousands or hundreds of thousands of publishers here, and you don't need to have a lot of computing resources on the publisher side of things. The consumers also, they can be simple web browsers, simple mobile applications, for example, that they can display the data gathered by pulling messages from these communication queues. Uh, and there's also, of course, a model where you have an exclusive pair connection between a client and the server. This is, again, a model which is very similar to what's happening in the internet, where you have this communication model and you have multiple handshakes between the client and the server. And basically, if you want to establish a very reliable communication channel between the server and the client, you need to do first some handshaking. So you need to set up a connection. The client requests the server to set up a connection. The server responds with an accepting request or with an error or something like a rejection if through by some reason or another it cannot connect to the client. And then you have the actual messaging from the client to the server and vice versa. And then you have the final stage of closing the connection between the client and the server. And this is very familiar maybe to you because you've implemented such things when you've connected to I don't know, UDP or TCP socket. This is handled by the connection protocol in the background. So these are the main models that we have adopted in IoT. Now, these usually come with different APIs. So I'd like to focus further on the way that IoT is structuring communication APIs. And there are a few particularities for IoT communication APIs, which I think are good to actually be mentioned here. So usually IoT employs REST as architecture and the philosophy for communication. REST comes from representational state transfer. It's an architectural style, software architectural style that was initially created to guide in the design of the architecture for the web, the World Wide Web in general. So as such, it defines a set of constraints for how the architecture of a distributed system, such as the internet, so a very large-scale distributed system, should behave. And it emphasizes on scalability and interactions between different components. Uh, it's a way, basically, for two computer systems to communicate, and it has HTTP as its main transport protocol. So it's very similar to how web browsers and web servers communicate, because it actually depends on the architecture that was established when the World Wide Web was founded back 30 years or so ago. So there are a few considerations when you are talking about REST APIs in general. And these are, let's say, client server particularities. Uh, One is the client does not care about how data is stored at the server. It just interrogates the server of data, and the server actually responds with a message packet or an error whenever the client interrogates it. And the server does not care about what the client is or what the user interface of the client is, or exactly. So the server just responds with the response to the request of the client, and that's that. So it's very simple in this regard, and it's stateless. Uh, it's stateless in a sense that the client does not actually hold any information that is more than what the current communication is about. So it doesn't have a history, or it doesn't go through different states of communication. The client request usually should contain all the information necessary to respond to a request from the server. So you don't need to be basing your messages on previous communication. It's also cacheable. That's very interesting, because you can actually cache these messages on a server or on a web cache before you can reply to them. And it's layered. So the requesting client does not need to know where it's communicating, uh, uh, whether it connects to a server, to a proxy, or to another intermediary. All you need to know actually is if you get your data or not. So it's stateless, and it's also layered in this respect. Uh, you really have no way of knowing that when you're interrogating a server, you're actually communicating to the server, or you're communicating through a proxy. Uh, so this is the, let's say, main structure of how a REST-based API functions. So you have a, let's say, REST-aware HTTP client somewhere in your network, and you communicate through methods which are very similar to HTTP packet methods. So you have methods such as get, put, post, delete, and so on. And usually the payload of a REST message is done over a JSON object or an XML. So it's formatted in plain text. It's very easily readable by a human operator. And it's got similar methods to HTTP requests. So the minimum, so to speak, of methods that you can implement over a REST API are get and put. So you send data and you receive data over this API. But of course, you can have multiple other methods similar to HTTP. The next step would be to actually undergo a server authorization. So whenever you request or you actually send such a HTTP packet to the server decides whether to reply or not to your message. So it can actually opt to reply to get messages, but it can opt not to reply to, I don't know, delete messages or post messages from the client. So you have this RESTful web service, which is aware of these messages and can actually post or uh, actually manipulate data in the favor of the client. And this is usually connected to resources, and resources are given through URIs. So it's a very basic method of actually requesting data from a server, which is very similar to what a web browser does. So, for example, how does an endpoint URL for such a server look like? Well, it could look like something like this. So it's a HTTPS my domain user 123, for example. And you can have also specify for the format in which the data is sent. So it can be, I don't know, JSON or XML. You have these four main HTTP methods, which usually are implemented by all RESTful APIs. So you have GET, which is similar to read operation. So in action, whenever you send the GET message, you would actually be expected to return the requested data. So the server would return you a packet of, I don't know, requested data. Might be temperature, might be some sensor data, might be a plain text, might be something else. Post is a create message. So whenever you send a post record, you create a new record in the server. Put, or might be patch, but usually it's put, it's an update message. So you overwrite or you update an existing record. And delete, of course, deletes an existing record on the server. Now everything is packaged in through HTTP. So you have HTTP headers, you have body data similar to an HTTP message. So for example, a GET request to, I don't know, slash user on your server might return a list of all the registered users on your system, for example. Or a post request to user uh, slash 123, it can create a user with the ID 123 using the body data in the message. A put request to the same URL will update user 123 with the body data again in the put message. A GET request to the same URL will return the details of user 123, and the delete request will eventually delete the user 123. So again, it's a very simple way of writing and reading data, updating data, and then deleting records on a server. And like I said, it's totally up to the server how to reply to these requests. So it might choose to actually perform this request, for example, a GET, or it might choose to ignore a delete request. Might be that you can create users on a server, but you cannot delete them, or you cannot even create them. It's totally up to the application how it handles this. Any questions so far? Okay, so the way the servers replies or the server replies is usually through a response payload. And this can be whatever is practical. Usually it's an HTML message, but it can also be data. It can be, I don't know, different files, images, audio files, so on. So typically it's JSON encoded, but you can also have XML encoding for your data, or CSV, or even simple strings. It's totally up to you how you actually structure this message, this response message. But of course, whenever you're designing such an API, you need to make sure that you have a uniform protocol to actually format this data. Um, Usually, the response is accompanied by an HTTP status code. So it could be 200 OK, which is used in successful requests. 201 created whenever you create. So whenever you see you have a post request, for example, here you might get a 201 created response message from the server, and then you have error messages. 400 bad request, 404, or 401, depending on the type of communication and the type of message you've sent. Now, this is all based on WebSocket communication between the client and the server. And whenever you have a WebSocket-based communication, you usually have this communication protocol in which you have first a handshake. So the client requests to set up a WebSocket to the server. If everything's okay, then the server will accept the response, and then you have data being sent between the client and the server after the connection has been established. And then if the client wants to actually break the connection, can actually post a request to close the connection, and the server accepts closing the connection. So it's again, a simple handshake protocol to establish a connection, and then you have data being sent bidirectionally between the client and the server. So there are different, let's say, IoT levels. What does an IoT level mean? It's a level of complexity when implementing an IoT service or a different IoT application. And we will go through the, let's say, main IoT levels that an application can have. Just structure them as, uh, let's say, different systems that are more and more complex. But usually you have three entities within an IoT deployment template. So you have a device or multiple devices, and these IoT devices, they allow identification. So they usually have some sort of unique identifier or an address. They typically allow remote sensing, so they usually have some sensors on them that can be read and can be periodically accessed. They might also have some actuation in them. So actuators might mean relays, might mean, I don't know, different motors, things like these. And they have probably remote monitoring capabilities. So you can remotely connect to them, and they can offer you the sense data in some sort of fashion through an API. You have resources. These are software components of the IoT device. They are for accessing, for processing, for storing different sensor information, or for controlling your actuators. So resources are the software components that enable the device to be accessed through the network. And then you have a controller service. This controller service is the one that runs on the device itself and interacts with the web services that are, on one server or connected through some sort of network or the internet. So the controller service, it sends data from the device to the web service and receives commands back via web services. Now, if you are looking at the website of things, you can have databases connected to your IoT network. They can either be local or stored in the cloud, depending on the level of complexity of your IoT system. You can have analysis components. These are in charge of analyzing the IoT data and generating results. You can actually use them to parse different sensor data or aggregate different sensor data over maybe a long period of time, and then give you a result which is, let's say, easier to understand from the user perspective. So they can work with big amounts of data. They can do signal processing. They can do data analysis. They can employ maybe different machine learning algorithms, and then they will actually give a result which is more easily understood by the user. Uh, you have also, or you can have also, they're not exclusive, web services. These serve as a link between the IoT device and the application or the database or the analysis component. So you can implement them using the principles that we've shared in the previous slides. So REST services, or using WebSockets. And then you have applications. These applications, they provide an interface that the users can actually adopt and control, monitor different aspects of the IoT system at large. So applications usually allow users to monitor the system, so to view its status at any time, and then view the results gathered from the analysis components, and then also take some actions within the network. So maybe actuate or I don't know, arm the system or uh, do some sort of action that will actually adjust the one or many components of the IoT network. So going through the levels, we will start from the lowest level possible, so or the simplest IoT application possible. And then we will, let's say, expand on this and bring more complexity to the application as we move up the level ladder. So the first level, or IoT level one, so to speak, is a system that has everything stored locally. So there's no cloud component to this system. And you have a single node or device that performs sensing and actuation. So it can monitor data, and it also can have some actuation. You can have some, I don't know, relays or motors there that drive some items in the real world, and it also stores data, and you can also perform analysis on the set data, and you also host the application. You do everything locally. So these are very suitable for modeling very low cost and low complexity solutions where you don't have a lot of data to be stored. So you can store the data locally. We're not talking about, I don't know, terabytes of data. We're talking maybe about, I don't know, hundreds of megabytes of data or even gigabytes of data that you can easily store on a local hard drive that is connected to the IoT network itself or the monitoring node. So you don't have any computationally intensive tasks in this network, and you have one node or let's say a very limited number of nodes here. So usually you have this monitoring node which performs the analysis and maybe stores data internally. And then you connect the device to, or you have kind of like a connection to a local server which hosts the controller service, the resources. It can actually interact with the database which is stored locally, and then you have the application. The application usually connects through RESTful or WebSocket services to the database, and you can actually see or inquire about the state of the monitoring node. So again, very simple, very easy to be implemented, and very low cost. Now, IoT level 2 is a system which has some cloud components. So if you see from this example of level 1, we've moved a few components to the cloud right now. So you still have a single monitoring node that can perform sensing and actuation and some local analysis, but also you have some cloud storage. So data is sent from the node to be stored in the cloud. Maybe you have a higher volume of data, or maybe you prefer storing the data in the cloud to have, let's say, more availability for your data than you can offer from a local storing service. And you also have the application and the database connected to the cloud storage also stored into the cloud. So again, higher availability than storing the application locally. Maybe here you have a higher quality of service because you can connect multiple clients to the web application, which is in the cloud, and you can have data available at any time, even if at times the connection between the monitoring node and the cloud storage is not available. You still have available the full history of data, which is stored in the cloud. So it's suitable whenever you have usually big data involved. Big data meaning in this context maybe more than simple gigabytes of data. Maybe you have terabytes of data or more. And the requirement is not, however, very computationally intensive. So you can have computation done locally, so you still have the controller service, the resource, and the device itself local, and you do all communication and computation, sorry, you do it locally, but storage is done in the cloud. Now, moving on to level 3, the difference between level 2 and level 3 is that you move the analysis component also to the cloud. So again, you have a single node, data is stored and analyzed in the cloud this time, and the application is also cloud-based, so this hasn't changed from level 2. You can employ such a solution whenever you have, of course, a large volume of data to be stored, and the analysis requirements also are computational intensive. So you might not want to do computation or so much computation on the monitoring node itself. Might be that uh, either the computational capabilities of the node are very low, so you cannot actually achieve a lot of analysis in a given time on the node, and it might mean that the node itself is has limited energy availability, so you can have the nodes actually, I don't know, powered by batteries. So you would not want to deplete the battery of the node through very intensive computation events. So you just prefer to send the data to the cloud and then offload any computation in the cloud from the device itself. Level 4 comes with even more added complexity. So instead of a single node, now you add the complexity of having multiple nodes to your network. So you can have, more than 2 basically nodes in a network. You can actually have the same paradigm of cloud storage here, but going a step back, the nodes, they perform the local analysis just like in level 2. So you have multiple nodes that perform local analysis, but you have data which is stored in the cloud. So everything such as the app and the database are also stored in the cloud, but you have also some local components here, which are typical to the nodes themselves. These systems are usually suitable for whenever you have multiple nodes in your IoT network, and you have a high volume of data which is actually being gathered or manipulated by the nodes, and the analysis requirements are not so computing intensive. So you don't need to actually employ a very intricate algorithm or something which is very computing intensive to actually get your results from the data. Now moving on to level 5. Again, you add some more complexity to the network itself. So if in level 4 you had multiple nodes, now you have multiple nodes that perform different functions. So you can have router or endpoint nodes, which are, let's say, the endpoints in a tree architecture in which you have also coordinators. So a coordinator node is responsible to collecting data from end nodes and sending that data to the cloud. So you don't have a single hop from the actual nodes to the cloud storage. You do this through a gateway or coordinator node. And again, analysis is not done here in the nodes themselves. So analysis is done in the cloud, where also data is being stored. So this is very similar to level 3 that we've discussed before, in the sense that analysis is not done locally anymore. These systems are suitable for solutions where wireless sensor networks are necessary, and data usually involves a lot of monitoring. So you have big volumes of data, and actually getting to a result from extracting a result from this data is computationally intensive. So you'd like to actually offload these devices into the cloud. Then you have level 6, in which As you can see, you have even more uh, even more complexity added to the cloud part. So you have multiple independent end nodes. They perform sensing and actuation. So you have an entire wireless sensor network here. They send data to the cloud to be stored and analyzed through these centralized controller nodes. Uh, the analytics component is also located in the cloud, and the results are viewed in the cloud-based application. Uh, Also, this centralized controller, which resides in the cloud, is aware of the status of all the end nodes. And you can send commands now to these end nodes, which in level 5 you could not do, or you cannot easily do. So level 6 closes the loop. You basically have analyzed data here, and you have the state of your network, but you also have a centralized controller which actually sends back control data to the nodes themselves. And whenever maybe it detects an erroneous condition, or it would like to change the behavior of a node, you can actually achieve that through a level 6 IoT network. Okay, this is, I think, the most advanced level of IoT implementation, and you can find more information on this book. It's Internet of Things: A Hands-on Approach. I've put the link here. It specifies all these 6 levels of IoT implementation and how they actually fit within the IoT paradigm, and how you can actually implement applications on these. Okay, so this was the lecture for today. Let's take maybe a, I don't know, 10-minute break, and then we come back for the lab. Okay.
Okay.
Thanks. See you in 10 minutes.